the last thing that I normally do, and I'll do a slightly abridged version of that, is that we talk about the sort of entropy and energy effects that go into phase diagrams that you see show up, so that hopefully when you look at a phase diagram or phase stability in general, you don't just see it as something empirically thrown at you, but often it's easy to rationalize. So the part that I'll talk about is the temperature behavior in a phase diagram. So phase as a function of temperature. And the only thing that thermodynamics really tells you is that if you have some transition between a low temperature phase, let me call it alpha, and a high temperature phase, and I'm sort of sketching this here in a sort of simplistic way because there will be in reality a two-phase region. What you know, so this is temperature. What you know from thermodynamics, the only thing that you really know is that the entropy of the higher temperature phase has to be equal to the entropy of the lower temperature phase. And that's because the temperature derivative, right, of free energy is minus the entropy. So if you think of a phase transition in temperature, right, so like you have this here, the alpha phase and the beta phase, and this is their phase transition. By definition, the higher temperature phase has to be the one with the higher entropy. So this is all that thermodynamics tells you. It tells you the magnitude of the entropy, or the sign of the entropy change as you have a phase transition with increasing temperature. But coming back to the sort of original idea that we stated in the very beginning of the class, that thermodynamics doesn't tell you anything microscopically. You have to infer that by knowing things like statistical mechanics and physics of phases of what might cause this entropy. So I want to go through that. So what are the sources in materials of entropy? And this is maybe a good review as well. In general, they are configured, you know, when things can share lattice sites, right? So when they can swap lattice sites. And we made a model for that. If they randomly swap, right? If occupancy of each side is random, then you have ideal solution entropy. But in many cases, it's not random, so the entropy would be less. With Chris Bartel, you've talked about vibrational entropy. And again, that's related to the vibrational excursions, right? So you generate entropy whenever you have a subset of the energy degrees of freedom that can go to higher energy. And then there's a third one, which I don't think we've talked that explicitly about, although you talked a little bit about in statistical mechanics. There can also be electronic entropy. Right? The fact that the electrons don't necessarily have to be in their ground state, but can occupy higher orders, higher energy states, and that means that leaves some low energy states unoccupied. So the probability of occupation becomes different from 0 or 1. So in principle, there's also magnetic entropy. I mean, if ions or atoms in a solid have a spin, a magnetic spin, right, that can point in different directions, which generates entropy. Often that's counted as part of magnetic, because in the end, the magnetism comes from the electrons, but from their spin, but you can also separate that out. That's not particularly important. And then if you go to non-condensed matter, so where you lose translational symmetry, you also have translational entropy, and that's the best example of that is for an ideal gas. This isn't a perfect division because in some sense, when you go to an ideal gas, these two, configurational and vibrational, become translational, right? So they are not sort of, they don't all exist together, because a gas doesn't have, it has intermolecular or intramolecular vibrational, but there's no vibrations between the different molecules. So these two take the place of that one, and that's sort of a somewhat more complicated discussion. So if you want to understand what happens to materials as you raise their temperature, what causes phase transition, essentially to get a high temperature phase to be stable, one of these has to become dominant, or all of them together has to become dominant over the low temperature phase. So I'll show you some examples where you can explain phase transitions by just one of these. The most common, of course, is configurational entropy, right? Because that's the one that you think of most of the time when you think of high temperature behavior. Because configuration is what's responsible to the intuitive concept of disordering, right? And what does disordering mean? That things starts to occupy the place in a lattice or in a liquid that otherwise would be occupied at low temperature by another ion. So always, if you take the configurational part of the entropy in a disordered state or a random solid solution, it is greater than the entropy, the configurational entropy of the ordered state. Or what that means is that if this is the dominant entropy term, you will have a phase transition. Sorry, I'm drawing this the wrong way. This is G versus T. You will have a phase transition between an ordered state and a disordered state, right? Because the disordered state has the higher entropy, and therefore it appears at higher temperature. And this is what you see in many phase diagrams, right? We've shown many examples of that. Let me actually go back maybe to the iPad and show you a few. This time I will remember to share it. Okay, for if you can't. Okay, where did I go? Okay. Oh, here, for example, the copper-gold phase diagram, right? So at low temperature here, you have ordered states. These are compounds, but with some of stoichiometry. It's a little messy, but basically the single phase regions are kind of like these guys here. And at high temperature, they disorder, and so you get a disordered solid solution. Again, this is quite common in systems. And again, this entropy is mostly what's responsible for your intuitive idea that if you go to high temperature, you get better miscibility, right? Because what does miscibility mean? Miscibility means that two types of atoms or molecules can occupy each other's space and each other's position. And that is dominated by the configurational entropy. The role that the other entropies play is maybe a little less intuitive and can vary a bit more. So what does vibrational entropy do? Vibrational entropy is actually in general much larger than configurational entropy. And you can look at that, right? If you think of, remember that the heat capacity is the temperature derivative of the entropy. The vibrational heat capacity is what leads to the law of Dulong-Petit, that the heat capacity goes to 3R, which is order of magnitude like 25 kilojoules per mole per Kelvin. That's actually much larger than what you would in most cases get by taking the temperature derivative of configurational entropy. But because it doesn't vary so much between phases, it tends to be not so dominant in phase diagrams. But in some cases, you see it show up. And to remind you how vibrational entropy works, I mean, in principle, you have to calculate the whole phonon spectrum and integrate that with their occupancy and get the entropy from that. But you can get sort of a rough sense if you know the basic frequencies in the material. And as you know, if you take an Einstein model of a material, then there's only one frequency you assign to every vibration in the material, because the energy levels are proportional to that frequency. And the frequency itself is proportional to the stiffness of the bonds over the mass. So if you have high stiffness, you get high frequency, right? If you have low stiffness, you get low frequency. So if you compare sort of like high stiffness solids so let's compare stiff solids with a high modulus and then do softer. So in a stiff solid, omega is high, so the energy levels are very much separated. In a softer solid, omega is lower, and so the levels are less separated. So which of the two will have the higher entropy? It will be the one with the lower separated energy levels. Because here because the occupancy is proportional to the energy away from the ground state. So here you will have a lot more sort of partially occupied levels, right? You will have a lot more levels occupied, which means your probability distribution is more homogeneous, so you get higher entropy. So here you get the higher entropy. If you think of that as complicated in terms of energy levels, you can also just think about it that a softer solid will have more vibrations. It will have more lattice vibrations. So you will have more excursions away from the ground state energy. So you therefore will have higher entropy. Okay. So what that means is that in some cases in phase diagrams, you will see a phase transition from a stiffer phase to a slightly softer phase. And the way that often shows up in condensed matter is that you go from close packed phases to less close packed phases. So in many cases, you will see things like FCC to BCC. Because FCC is close packed, BCC is not. So BCC, because it's is not as close packed, tends to be slightly less stiff. So it tends to have slightly lower elastic constant. And so you'll often see transitions like FCC or HCP, which is as good as close packed to BCC. Those are sort of the simple phase transitions, right, in elemental metallic systems. But you can see this show up in more complicated solids as well. So let me show you some examples of that. Okay, let's see. We had a few here, right? Okay, here's a good example. Titanium. So titanium at low temperature, the alpha form of titanium is HCP. And then the high temperature form of titanium, the beta form, is BCC. So this is a classic vibrational entropy driven transition. You may wonder why are there all these polymorphic transitions? It's because the ground state energy of HCP and BCC titanium is close. It's close enough that at high temperature, the fact that BCC is slightly softer and has higher entropy can make it appear. Another interesting example is iron, and I've only shown the high temperature part here of iron here, right? Because gamma iron, this is iron carbon, by the way, phase diagram, but gamma iron is FCC and delta iron is BCC. And again, this is a transition here that is vibrational entropy driven. The strange thing about iron, of course, is for those of you familiar that if you go way down here, somewhere below here is again BCC. So that seems to violate my my principle here. But turns out this BCC is actually magnetically stabilized. This is actually ferromagnetic iron. And this is a particular electronic reason. But this transition here, this is essentially delta S vibration stabilized. So those are the two easiest ones to recognize in phase diagrams. The one that's a little trickier are the one that's a little trickier is electronic. First of all, how would you think of electronic entropy? You know, remember from statistical mechanics that when you sum a multi-particle system, you can either sum over the particles, right, what the partition function is of each particle, or you can sum over the states, right? So when you decompose the partition function, you can decompose it as the partition function of particles if they are independent, or you can decompose it of the partition function of states if the states are independent. And what would you do in the case of electrons? If I ask you the partition function of a many electron system, would you decompose it into the partition function of each electron and multiply that? Or would you decompose it into the partition function of the states?
States.
Yeah, states, right? Because electrons is probably the best example of where the partition functions of each electrons are not independent. They are actually, first of all, strongly interacting, but they are even more interacting because of the Fermion Principle, right? That every state can only be occupied. So it's an extremely strong, can only be occupied by one electron. So it's an extremely strong form of interaction, right? It's really saying, well, if your electron occupies this state, even if my electron doesn't have any physical interaction with it, it can't occupy that state. So the occupancies for each electron are strongly dependent. So on the other hand, the states, the one electron states are eigenstates, so they are by definition independent. So if you're going to calculate any property of electrons, you're going to calculate it as a sum over states, not as a sum over electrons. And so the same is true for the entropy. So how would you calculate the electronic entropy? I'm going to normalize it by the Boltzmann constant, right? So you can calculate it through the Gibbs formula, right? The Gibbs formula would normally that, you know, you sum over states and you do pi log pi. Right? So what are the states here? Well, I'm going to do this by an integral over the density of states. So this is the DOS, right? The density of states, of electron states. I'm going to integrate over the energy, so I capture all the states. And what goes in here? What's the pi log pi? Well, a state can either be empty or occupied. So really what I have to sum is the probability that it's occupied times the log that it's occupied, log p occupied, plus the probability that it's empty, which you could say is 1 minus p occupied, log 1 minus p occupied. So if you integrate that from minus infinity to plus infinity, you would get the electronic density of states. Sorry, the electronic entropy. Does that make sense, right? I've sum over all the states I can have for this system, and I sum the occupancy probability. And the good news is that for an electron system, you know what the occupation probability is, right? This is the Fermi-Dirac function, right? This is the Fermi-Dirac function. which I'm sure you remember how it looks like, right? So it turns out in many cases, so you can do that integral if you know the density of states, but because the Fermi Dirac function is so well behaved, in many cases the result is actually a lot simpler, or can be simply approximated. So let me draw density of states. So let's say this is the density of states for a material. And I'll do my best. Density of states is always a bunch of squiggles, right? There we go. That's my density of states. That's my density of states. So let's say my Fermi level is here. Then how does the Fermi Dirac function look like? As you know, below the Fermi level, it's 1. Above the Fermi level, it's 0. And there's sort of a narrow sliver. So now I'm going to, this is a different axis right now. I'm drawing the Fermi Dirac function. So it's basically flat. It sort of goes down, right? And then sort of becomes 0, right? And it's sort of one half at the Fermi level. So whenever the occupancy, which is the Fermi Dirac function, is 0 or 1, this integral vanishes, right? Because the P log P piece vanishes whenever the probability is 0 or 1. So the only contributions in this integral come from this part, right? This part where the Fermi Dirac distribution function. So this is the only contribution to the electronic entropy, where the Fermi Dirac distribution function is different from 0 or 1. And then I can kind of approximate, right? Because we know what this width is, right? This width is of the order of KT. Okay, so the number of states, roughly the density of states at the Fermi level, times kBt. So the number of states that appears in the integral, right, where this integral is non-zero, is basically of the order of kBt times the density of states at the Fermi level. And I've neglected what P log P is there because basically P log P is going to be of the order of 1, right? So what you see is that the electronic entropy, you know, scales with the temperature. That's because this window opens up as the temperature goes up, right? But depends on the density of states at the Fermi level. Because if you have a high density of states in the Fermi level, you can do a lot of excitations across the Fermi level. If you have low density of states there, you have low excitation. So if you do a more exact theory, where you actually kind of integrate P log P and everything, you find that S electron over KB is pi squared over 2. Pi, of course, has to appear everywhere. KBT times the density of states at the Fermi level. And you know, we're not that far off, right? Because pi squared is about 10, right? So 10 divided by 2 is about 5. So we are in the right order of magnitude. But the important thing is to understand that the electronic entropy depends on the density of states at the Fermi level. And you may have sort of heard that before because the temperature derivative of the electronic of the entropy, right, is the heat capacity, right? If you remember, T times ds dt is the heat capacity. And again, that also scales with the density of states at the Fermi level. So why is electronic entropy often neglected? It's because whereas for other entropy contributions, all the atoms participate, right? If you do vibrations, all atoms participate into creating vibrational entropy. The same with configurational. For electrons, that's not true, right? Only the ones that occupy states near the Fermi level participate in the electronic entropy. And that's actually a very small fraction. If electrons were not fermions, let's dream up some imaginary world. If electrons were not fermions, but let's say electrons were bosons, then what would the entropy be? If the electrons were bosons, then what would the electronic entropy be? Or what would the heat capacity be? Electron entropy or heat capacity, you can give me anything. Think of it in the high temperature limit. What is the heat capacity of bosons?
Would it be constant because they'd all be in the bottom state?
No, at high temperature. Right. So at high temperature, basically, heat capacity always goes to half a kBT per degree of freedom, right? Well, half a kB, right? So if electrons were bosons, you would have in the heat capacity of the order of n electrons, depending on how many degrees of freedom you think an electron has. So let's leave that out, whether it's 1/2 or 3/2, I don't know. Doesn't really matter. But you would have n electron times kB for the heat capacity, right? This number would be very large, right? Because you think you take an, I don't know, your average metal with 20, 30 electrons, let's say a transition metal. So if electrons were bosons, this would totally dominate the heat capacity, right? But they're not, right? Because of Fermi Dirac, most of the electrons don't play, right? All these electrons here don't participate at all in the entropy. Where electronic entropy may be important. So let's do a game of high or low. What about metals? Entropy high or low? I know it's kind of not fair to ask you back because I'm not giving you a reference, right? What high and low means. So typically we think of metals as low to medium electronic entropy. And the reason is, of course, by definition, for a metal, the density of states at the Fermi level is non-zero, because that's what gives you conduction. But it also tends to be not super high. And the reason is that states in metals are spread out over very large energies, right? Because they have very high bandwidth. So you tend to not have major spikes at the density of states. Well, by definition, if you have a band gap, you have no electronic entropy, right? So if you have valence band and conduction band, and your Fermi level is here, and this band gap is large enough, you have no electronic entropy, right? So in insulators, the electronic entropy is basically approximately zero. Even in semiconductors, where you have some excitations across the gap because of dopants, the number of dopants is usually so small compared to the number of atoms that the electronic entropy of semiconductors does not participate in its thermodynamics. I'm not saying that those excitations aren't important, because they're of course important for generating conductivity, but they're not important from a thermodynamic perspective, because doping concentrations are like 10⁻⁶, 10⁻⁸, whatever, right? So it's only sort of 1 electron per 10 to the 6 or 10 to the 8 atoms that generates entropy. I realize I'm going here between characterizing solids by their properties and by their chemistry, but if I ask you about oxides, I mean, oxides is a chemical class, whereas the other ones are sort of categorized by their conductivity. What do you think about oxides? Do you think they would have low or high electronic entropy? Ah, we should have done polls. I forgot to set up polls. Signs by majority. So it's a bit of a trick question, right? Because oxides can kind of live in both of these worlds. So obviously many oxides are insulating. Take aluminum oxide, Al2O3, or take ZrO2, zirconium oxide, right? So in many cases, they're insulating. The insulating ones definitely have no electronic entropy, right? But they're also conducting oxides. And that's where it gets a little messier. So, and some are good, you know, you can make metallic oxides, right? Like reduced titanium oxides, or you can take oxides where you have hopping conductivity, right? Polaronic conductivity, where an electron sort of hops from side to side. So not like in a metal where it tunnels from side to side. And there it gets a little messier to think of the entropy. So I'm branching a little out here into other courses you have, but consider it to be like general education and prep for your prelim. So if you take a conducting oxide and you compare it to a metal, let me a vector K, right? This is basically what you call bands. So metals have a lot of bandwidth. Let's say this is the Brillouin zone edge, right? So let's say this is a metal. And this is, remember that a band contains one state or two states, depending on how you count electron spin. So that means that each little piece of this band is only actually a very fractional state. So if your Fermi level is here, sort of the piece around the Fermi level, which is the density of states around the Fermi level, is actually very small. But how do the bands of an oxide look like? By the way, what sets the bandwidth? The bandwidth, by the way, is this thing, right? It's what's called the bandwidth. The difference between the low part of the band and the high part of the band. In terms of sort of bonding, what sets the bandwidth? It's the orbital overlap, right? The wider the orbital overlap and the closer the energy levels of the atoms themselves, but it's mostly the bandwidth that set the orbital overlap that sets the bandwidth. And that's why in metals, right, where you're overlapping S states and P states, which are quite wide, you have a lot of bandwidth. So how does the density of state of an oxide or the band of an oxide look like? Well, it's in general much, much narrower, because in oxides you're overlapping, you know, metal state with oxygen states, which have not nearly as much overlap. So often the bandwidth is extremely narrow. So this is sort of in contrast, say, the bandwidth of an oxide. So what do you think, given that, what do you think about the density of states? It's going to be much larger, right? Because think about it, one band contains one state. So if I take just sort of an interval dE in here, it it contains a lot more states. So oxides have a much higher density of state at the Fermi level, unless the Fermi level is in a gap. But when an oxide has actually metallic-like conductivity, it will actually have a higher entropy than a metal. Okay? So where does this break down? What if this band becomes completely flat? I'm warning you, this is Professor Ramesh's favorite question on the prelim. This is what I'm telling you. But he won't put it in these words. So what happens when I have a flat band? So something has to be wrong, right? Because my theory here would say, well, if I have a flat band, I have infinite density of states at the Fermi level. And I would have amazing electronic entropy. But what goes wrong? So what happens to electron states when I have a flat band? So what happens is that the band picture is wrong, right? So you have no block states anymore. So when you have no bandwidth, and if you think about where does that come from, right? If I have no bandwidth, that means I have essentially extremely small overlap between orbitals. It's almost non-existent. Which means that actually electrons don't really tunnel from state to state, right? I mean, what is hybridization? What makes bands? Is tunneling, right? If an electron tunnels really fast from atom to atom, you get bands, and you get this metallic-like conductivity. If you start crimping down the bandwidth, which is the orbital overlap, basically the tunneling rate goes down and down and down. And at some point, what happens? If the tunneling rate becomes extremely slow, let's take some extreme. Let's say the tunneling rate is a second on average. So it takes a second on average before an electron tunnels from band one atom to the next. So at that point, the electron localizes, because basically what happens is that the electron sits on an ion. The structure has more than enough time to relax around it, right? It feels an electron. I'm going like, I'm going to adjust my size or whatever, right? Because if I have an electron, I'm bigger. And so you get what's called a polaron. You get trapping of the electron. So at that point, band picture is completely gone. So you get localized states, right? And this is sometimes what's called, the word you want to remember if you talk to Professor Ramesh by accident on your qualifier is things like Hubbard localization. I'm totally giving his questions away. He describes it like a traffic jam. You know, you can't move fast enough from spot to spot, right? I mean, traffic is a bit like that, right? If you think of traffic as moving your car into a vacancy, right? Think of a freeway, right? If there are low amount of vacancies and they're not moving very fast, then you're kind of hopping from vacancy to vacancy with your car. If there are a lot of vacancies and you're moving very fast, then you're kind of tunneling across the freeway, right? You're never really staying in one spot or in a vacancy. So I think that's his analogy. So if that comes up, like, let me give you an example of this. So a famous case of high electronic entropy is the perovskites family, lanthanum manganese oxide. So these are perovskite, right? This is the A side. This thing, lanthanum, is 3+, manganese is 3+, and so 3 oxygens give you 6-, so it's charge balanced. So you can carrier dope that by doping strontium on this side. So you make lanthanum, strontium on that side. And then what you get here is mixed manganese 3, manganese 4, right? Because strontium is 2+. So whenever you put 2+ here, you need to have higher charge on the B side, O3. So this system behaves fully localized. So while you have a mixture of manganese 3 and 4, and that's actually where the Fermi level sits, you might think you have a metal, right? Because you're in a half-filled band, right? Maybe you're on average 3.5. Let's say I have 50% lanthanum, 50% strontium. I would on average have valence 3.5 here. But it's not a metal. What it is like a lattice where you have some, let's say these are the manganeses, right? Where you have some 3 pluses, some 4 pluses. And they're fully localized. So the valence of the manganeses is not 3.5, it's really 3 and 4 mixed together. So how would you calculate the configurational entropy of that? I told you the answer. Duh, it's configurational, right? So here, the electronic entropy by localization has become purely configurational. This thing has entropy simply because the 4 and the 3 can kind of sit on each other's side. So this is, again, you would calculate this just by doing combinatorics. And if I told you this distribution was random, then it would just be x log x plus 1 minus x log 1 minus x. It would be the ideal solution entropy, which is much larger than metallic entropy, right? Because in metallic entropy, only the carriers at the Fermi level matter. It depends on the density of states at the Fermi level. Here, I have participation of 1 carrier for every manganese. So this entropy tends to be much larger. So this is an oxide with high electronic entropy. So there are practical applications of electronic entropy. You can do a fairly straightforward proof that the electronic entropy relates to thermoelectricity. And if you think about it, it makes some sense, right? If you want to couple heat flow and a potential, right, you need the partial molar entropy of something that's charged. And so an electron is the relevant quantity to generate thermoelectricity. Because you should actually try to do this. If you can do this, you're golden, right? Then you're set in thermodynamics. If you can calculate an equilibrium between a piece of metal at two different temperatures in the two ends, the only thing that you can move is a charged species, which is the electrons, right? And this is how you set up thermoelectricity, because thermoelectricity is the coupling between either a temperature gradient and a heat flow, or an electric potential difference and a heat flow. And so, for example, metals are medium thermoelectrics, right? This is how you make a thermocouple. I mean, those of you who do experiments, you may have all used thermocouples, right? They are used not because they're such great thermoelectrics, but when you measure temperature, you don't really need a super large voltage for a temperature gradient. You just need to be stable. But all the really good thermoelectrics, so the ones that generate a lot of potential for a small delta T, none of those are metals, right? They are all either oxides or chalcogenides, so sulfides and selenides, because they have the right combination of electronic entropy and electron conduction, right? Because to make a thermoelectric generator, you also have to conduct the electrons. Okay. Oh, let me show you something quickly. Until about 10 years ago, I had no idea how to look for electronic entropy in phase diagrams. It was really hard to detect. And then we came across some system, I think I have a picture of it, which has a remarkable phase diagram. It was actually predicted theoretically, but then verified experimentally. Let's see if I have it. Here we go. This is a remarkable phase diagram. This is the phase diagram of a battery material. This is lithium iron phosphate, and this is iron phosphate. So here, because you have a lithium ion, here the iron is 2+, and here the iron is 3+. At low temperatures, there's a miscibility gap. So these two states are not miscible. This is actually a two-phase region. It's called H plus T because one of the phases is called H, the other one is T. This is a two-phase region. And notice that it does look like Mickey Mouse ears, right? This phase diagram. That's what I always thought. That you would think that this looks like, if there hadn't been this dip, this sort of looks like a miscibility gap, right? Right? I mean, it's just like a miscibility gap. It turns out that this unusual shape, the fact that the disordered phase comes back in here, this is purely due to electronic entropy. So the electronic entropy is actually what causes the disordered phase or the mixed phase to come down to an extremely low temperature, highly unusual from this sort of behavior. So there's a high degree of electronic excitations in this phase, and so it looks quite different from the way we thought it would be. Okay, I want to show you a few more odd things. It also, sort of thinking about entropy in phase diagrams helps you explain which things are sort of, you should be skeptical about. They're not necessarily impossible, but let me show you an example. If I showed you a phase diagram like this, so now we're doing composition, temperature. So I have some phase here with a little bit of solubility. I have some phase here, right? And I tell you that what happens is that at a higher temperature, a stoichiometric compound appears eutectically. So this is gamma and it's stoichiometric. I think that's highly unlikely when somebody plots that. And why do you think that is? Could you reason through that? One of you is talking, but I can't hear you, so you might be muted. Think about
just like the compound should show up like low temperature, like like the compound phase diagram as we showed before. Is that because like for the compound phase, because its entropy is yeah, so I think it's just like it should show up below the eutectic point.
Basically, the statement we're making, right, is that sort of in this temperature region, that the compound of gamma, if this is correct, the entropy of the compound has to be greater than, you know, whatever is the properly weighted sum of, so some, I'll call it A times the entropy of alpha plus B times the entropy of beta, right? Where, you know, they have to conserve composition, right? So there's some linear combination. So, because think about it, at this transition just below it, I have some linear combination of alpha and beta, and above it I have gamma. And this is highly unlikely, because which entropy would make this would favor this, right? It's unlikely to be configurational, because I told you this is a stoichiometric compound, so it's probably well ordered. So this thing probably doesn't really have configurational entropy, whereas these two phases, because they start to develop some solubility, they definitely have some entropy, right? And the linear combination has some entropy. So it's unlikely to be configurational. What about vibrational? What do you think? Go with your guts, right? What do you think? Which do you think is the stiffer one? Which do you think has the higher vibrational modes? The compound or the end members? So in many cases, the compound is the stiffer phase. And the reason is that the fact that a compound actually forms right, means that there's some attraction between the atoms and that they make a stiffer, more strongly bonded material. Again, this is not a 100% rule. It's just sort of a 95% rule. And so it's unlikely that this is the vibrational entropy either. Again, I can't prove to you that it cannot be the vibrational entropy. There could be some very strange way that this material is actually softer, but in many cases it's not. And for the same reason, it's very unlikely to be the electronic entropy. Because compounds tend to have lower density of states than the mixture of the elements. And the reason is, again, because they have a favorite bonding, so they push states below the Fermi level that they fill, and they push states above the Fermi level that they don't fill. So this is an unlikely scenario, right? And I think, as you pointed out, much more likely would be the opposite, right? The compound at low temperature and something like this, much more likely. You know, again, I'm not saying this is completely impossible, but a bit odd. This would have to be something that has a real entropy benefit, right? So maybe if this were actually some kind of a solid solution in an unusual structure, but then it would probably develop. It would probably develop a lot of phase width. So it would probably much more look like this. If there's a sign that this thing is actually some disordered system, and that's what gives it the entropy. That's possible. Okay. Last thing I want to cover is how these different entropies can argue with each other and overcome each other. So in general, we are used to seeing, we are used to thinking of phase diagrams where some ordered state is below some disordered state, right? At higher temperature, you get more disorder, you get more mixing. And as I told you, that's because most phase diagrams are driven by configuration. Most phase behavior is driven by configurational entropy. It's not that it's the largest, it's that it changes the most between different states. But let's think about this transition. And what about the vibrational entropy? Do you think the vibrational entropy of a mixed state would be higher or lower than that of an unmixed state? Or an ordered state, not unmixed here, I have an ordered state. So let's say I do a simple thing like I take a compound titanium aluminum or so, and I can make it disorder, so it becomes a solid solution. Would the solid solution have higher vibrational entropy than the compound or not? It turns out that the answer is unclear. People used to always think that the solid solution had the higher vibrational entropy. But that has turned out not to be true when people investigated it carefully. People have investigated by doing neutron diffraction and getting the phonons. The idea was fairly straightforward. The idea was, well, you know, in a solid solution, atoms are not perfectly bonded because you don't always have the environment you really like. Whereas in a compound, every atom tries to get as much as possible the environment it wants for bonding. And so therefore, in a solution, you would expect the bonding to be somewhat less perfect, which is why it has the higher enthalpy, right? And therefore, you would expect it to be less stiff. Less stiff means higher vibrational entropy. So that's probably true like 60, 70% of the time. But there are now many solutions identified where the disordered state actually has lower vibrational entropy. So the mixture is of lower vibrational entropy than the solid. So the question is, can that difference become larger than the difference in configurational entropy? So can the vibrational entropy difference can it become larger than the configurational one? And of opposite sign. What would happen if that's the case? So again, the disordered state always has the higher configurational entropy. But let's imagine a situation where it has lower vibrational entropy. And the difference between the ordered and disordered state in vibrational entropy is actually larger than the difference in configuration entropy. Then the total entropy of the ordered state, right? If this is true, then the entropy of the ordered state is higher than the entropy of the disordered state. And so how does the phase diagram look like now? Phase diagram inverts, right? So now you have order on top here and disorder below. So there is nothing in thermodynamics that forbids this, right? Again, all thermodynamics tells you is the high temperature phase needs to have the higher entropy. It doesn't tell you anything about what that phase should be microscopically. The reason we think of this as disordered phases at high temperature is because our intuitive focus, somewhat unconsciously on configurational entropy. We always think of higher temperature mixing things better, but thermodynamics does not tell you that that has to be the case. In a world of only configurational entropy, that is indeed the case. But if you look at all these other entropic terms, that's actually not the case. And where does this happen? This rarely happens. Actually, to my knowledge, it has never happened in systems made out of atomic elements, so small molecule elements. But it happens in polymers. And the reason is that the configuration and the disorder and the vibration entropy scale differently. So polymers. Because what vibrates, right, is every atom participates in vibration, whereas the configurational entropy scales with the number of polymer chains. Right, so if you have a degree of polymerization, this is your polymer chain, right? And if you have n segments, then basically this is proportional to n, whereas this is just proportional to 1, right? For one chain gives me a certain amount of configurational entropy, because the configurational entropy in polymers is now the movement of the chains with respect to each other, which are large objects. The vibrational entropy depends on the number of constituents in that chain. And indeed, inversion of disordering is actually quite common in polymers. And here's, for example, a phase diagram of polystyrene with polymethyl vinyl ether. And what you see is actually inverted immiscibility, right? So this is the amount of polystyrene, this is the temperature. You now have solid solution at low temperature, you have miscibility at low temperature, but actually at high temperature, you actually have phase separation. And actually, you have an inverted spinodal even. Okay. And this is actually used actively in the processing of polymers to actually process them in very different ways. But this is essentially because polymers, their scaling of the different entropy terms is so fundamentally different than in solids that are made up of small molecules, right? Like atomic solids or molecular solids. The question is, can you go even further? So this is still two solids, right? This is solid solution. And this is two-phase solids. Can you go so far as to do this for the liquid? Can you create a liquid with lower entropy than a solid? So can you make a material for which the entropy of the liquid state is less than the entropy of the solid state? So is that possible? Well, first let's ask the question, can thermodynamics allow this? And of course it can, right? Again, thermodynamics doesn't make any statement about microscopic states. So it just tells you that whatever has the highest entropy comes out on top, right? That comes out on top at high temperature. So the question is, can you do this? And until like, you know, when I first started teaching thermodynamics, I always would tell the students, well, it's possible in principle, but I've never seen it. And then came some paper where they found it. I was going to share that with you. And of course, you can't do this easily with small atom solids, right? Because of the scaling of the entropy terms. But when you start to get to complex organics, okay, here we go. Here we go. So here's the paper. Actually, this is the physics web. It's from 2004. Tells you how long I've been teaching thermodynamics. It's the material is actually alpha cyclodextrine dissolved in methapyridine. So this is dissolved in and the reason that this is so odd is what happens actually that when you solidify, you get these glucose units that become very ordered, and there are then smaller molecules that rattle in the cages, and they have extremely high entropy. So this is a case where the solid state is allowed to have higher entropy than the liquid state, and so you actually have inverted melting. It's the coolest thing ever, right? So, you know, you cool something down and it melts, and you heat it up and it becomes solid. I don't know how far this field has gone, but my guess is now that we sort of understand how to do it, I think you could actually make plenty of materials like this, and then try to figure out what you're going to do with it, right? I'm sure that you could all come up with amazingly interesting applications for these kind of things. So, cool. That was it. That's all I have to say about phase diagrams. Let me stop sharing.